Hi, everyone. It's wonderful to be here in beautiful Cache. I'm Yan-Pei from Cal Berkeley, the Algorithm, Machines, and People's Laboratory, or AMPLab. I have the pleasure of telling you today some collaborative work we did with NetApp on empirical analysis of some enterprise storage system traces, where we do some objective statistical analysis and design some very specific, highly targeted design implications. So hopefully this will be fun. Okay, so the motivation for this work is really to understand data access patterns for storage systems. These are the kind of client and server storage systems that we analyze, multiple clients connecting to multiple servers. It's worthwhile to optimize for this kind of systems because they store mission-critical or crown jewels type data for a variety of companies across a variety of industries. Some of the questions that we may ask, for example, on client side, how do applications access data? How do users access data? On the server side, likewise, we can ask, how are files accessed? How are directories accessed? The guiding principle we have, or the faith that we have, is that better insights into these access patterns, they lead us to better storage system design. So to this stage, we have designed our large-scale storage systems more or less based on intuition and occasionally based on straightforward analysis of how systems behave. Now, these type of systems are getting more complex, so we have to start to question our intuitions, our mental models, our assumptions, and come up with a step up in the empirical analysis methodology. In other words, a more scientific and objective way of understanding how these systems behave and design accordingly. As I mentioned, we're definitely not the first to do trace analysis, so some of the improvements of our prior work. For example, we make a conscious attempt to minimize expert bias. So in this case, bias comes from our designer human mental models and assumptions about how systems behave and what matters for these systems. So the kind of assumptions we make about in our analysis, they ultimately determines what kind of information we are able to find. And if we have too many assumptions or we are not aware of those assumptions, that usually lead to incomplete or even worse, incorrect ideas about system behavior. We also do multi-dimensional analysis. Now, past work, they have also looked at analysis across many different dimensions. However, the analysis is often one dimension at a time. And when we start correlating across different dimensions or different ways of describing storage system, a manual analysis at best that can correlate only 2 or 3 dimensions. Now, we need multiple dimensions, again, because systems are getting more complex. We have many ways to describe them. There are many aspects to their behavior. So the ability to correlate them will allow us to get a more comprehensive understanding of what's going on, and therefore more specific, more targeted design optimizations. Also, we perform multi-layer analysis. Here, a layer means a natural semantic scoping of the storage systems. This is important because we consider both client and servers of these network-attached storage systems. If we analyze just one and not the other, then we get incomplete characterization of the system. So to give you a preview of what's to come, here's an example of a multidimensional insight. Files with greater than 70% sequential read or sequential writes have no repeated read or overwrites. Now, this is multidimensional because it covers 4 dimensions: read and write sequentiality, repeated reads, overwrites. It's helpful because one of those dimensions, sequentiality, we can measure very easily, and we kind of get the other dimensions for free. Now, these type of insights, as you'll see later on in the talk, they lead to very, very specific, highly targeted, threshold-based design optimizations. So the outline of my talk, I'll be telling you a bit about the traces we collect, the very large-scale enterprise system storage traces. I'll be talking about the analysis methods, the statistical multidimensional analysis methods we use to extract the common access patterns. And also, of course, interpreting the results and drawing some design implications. So we collected CIFS traces for some enterprise class NetApp storage systems. CIFS, it stands for Common Internet File System. It's the file system used by Windows. Those traces are collected at NetApp headquarters, one of our enterprise data centers, over 3 months. There's one corporate data set covering over 1,000 employees in various marketing, finance, administration, HR type roles. And another data set covering engineering employees. So these are 500 plus engineers in various software and hardware development roles. So we believe our analysis results should be relevant to other enterprise class data centers as well. The reason being, there is nothing special per se about the use cases at NetApp, and therefore the insights they should generalize to typical corporate administration and high-tech research and development type use cases. So to give you a sense of the scale of the traces, the corporate data set, as I mentioned, covers a variety of employees in different roles. They cover a diverse range of Windows applications, and as you can see there, order hundreds of thousands of user sessions and 1 million plus files, and likewise for the engineering trace. So the sense I want to convey is these are really reasonable scale data sets from which we can derive some results with a reasonable level of statistical confidence and have some idea that these are not just toy use cases. So the traces, they cover several semantic access layers. Now, as I mentioned before, semantic layer is a natural scoping for grouping data access patterns. And again, we need to look at them because the client's behavior, individual behavior, is different from the aggregate behavior across many clients at a server. Now, at the clients, we look at user sessions and application instances. So these are client-side, natural design, semantic scopings. At the server side, this should be more familiar, files and directories. The reason we can do this kind of analysis is in part because of the CIFS protocol. So the CIFS protocol, it contains information that allow us to identify these layers. So things like user ID, process ID, tree ID, file ID, they're all in the protocol trace we have. So now I'll talk a bit about so that was the traces, and now we'll do some analysis on these traces. So as mentioned before, we do multidimensional analysis. Reason for that, again, is because we have many ways to describe an access pattern. So for example, a file access pattern, to describe a file access, we can use I/O sizes, rewrite ratio, sequentiality, what directory it's in, how many repeated writes, overwrites, so on and so forth. The list goes on. Now, the multidimensional vectors spanning across all these dimensions, they make one data point. So one description of one file, if you like. Using multiple dimensions, it helps minimize bias. Again, bias comes from designer assumptions. So for example, if we want to reduce cognitive load, and that's really a concern in analyzing these complex systems, maybe we will start with a handful of ways to describe this behavior. Now, assumption about the system, that will heavily influence what dimensions we select. So for example, we might have some preconceptions about the I/O size and rewrite ratio and sequentiality. Those three are the only three that have an impact on system behavior. Now, the risk of doing that is, of course, we come up with incomplete or even worse, incorrect descriptions of how these systems behave. We're missing out on sequentiality, we're missing out on overrides, we're missing out on the directories access, different file types access, so on and so forth. So the way we attempt to resolve this is to start with many ways of describing a access pattern. And then we use some statistics, standard statistical methods to help us reduce the dimensions and help us identify which ways of describing the system actually matter. Doing so allows us to discover complex behavior. Again, manual analysis, they are limited to 2 or 3 dimensions. Now, as you will see in a few more slides, that this we employ a statistical clustering method that allow us to correlate up to tens of dimensions. So that kind of analysis is definitely not possible to do manually. We've attempted that, so we learned the hard way. Right, so the clustering algorithm, the particular clustering algorithm we choose is called k-means, and is essentially attempts to find natural groupings of data points in multidimensional space based on some idea of closeness. And for us, closeness is just multidimensional Euclidean distance. So the algorithm, that picture gives you a sense of the graphical intuition behind that algorithm. We start with a bunch of data points in multidimensional space. K-means choose a set of randomly chooses a set of cluster centers. Now the data points are assigned to the closest cluster centers. We recompute the cluster means based on assignments, iterates until the cluster centers converge, meaning they don't move anymore. So the way we apply this method is that for each semantic layer, in other words, for each for user sessions, for application instances, for files and directories, first we pick a large number of relevant ways of describing that kind of access patterns. Then we compute the numerical values across all these dimensions, apply the k-means clustering algorithm, trusting it the objective multidimensional statistic correlation there. Then we interpret the cluster centers that come out, multidimensional numerical vectors, and from that, we can draw some design implications with a level of confidence that we've covered the whole spectrum of system behavior and that they are targeted design implications. So for the rest of the talk, I'll illustrate this process by focusing on application layer analysis. So the question we want to answer is, what kind of applications access these file systems? So we select 16 dimensions, or 16 ways to describe an application instance, like so. So they contain some descriptions of I/O sizes, request sizes, the number of requests, something about inter-arrival patterns, sequentiality, repeated reads override, so on and so forth. So as you can see, it's a fairly comprehensive list. Now, the way we come up with this is we begin with the ones that we thought obvious. So this is at the stage where we were making our own design assumptions. We were not yet enlightened about this fact. So we start with a small number of dimensions. We do some analysis, then actually realize that the analysis doesn't tell us anything. Then we extend it to 20 plus dimensions, all of the ways we can think about. And that made us realize some of the dimensions are redundant, like arithmetically redundant. So we remove some and end up with 16. Now there's a level of subjectiveness in doing that, inevitable subjectiveness. But the multidimensional statistical method that allow us to also have the statistics guide us in choosing which ways are more important. So doing so give us 16-dimensional data points and order hundreds of thousands of application instances for each trace. Now, k-means helped us identify 5 clusters, significant clusters for each of the traces. The method we use to choose 5 clusters. Now, again, this is a standard statistical method, and you can use more, read more about it in the paper. Many dimensions were still correlated. So, for example, this is the output of the k-means clustering algorithm. So, multidimensional numerical vectors identify 5 clusters or 5 types of applications, and these are focused on the corporate application instance. So these vectors, they are sufficient for the systems to make some design decisions on. But just by themselves, they are a little bit unhelpful for us human designers. So the system can understand, cluster index 1, cluster index 2 have very much value in that many dimensions. But for us, humans, mere mortals, we want some additional info, and that requires additional interpretation. That's, in fact, the next section of the talk. So let's bring back this table, and we will attempt to label the application types. So for example, if we look at cluster 2, so right there, you may notice that this cluster, it does no I/O, so no read and writes. and it does a handful of metadata requests. None of the other applications type does this. So that's a distinguishing feature. And we choose to call that supporting metadata applications. So it's this kind of process. Let's do another example. So cluster 5. It does a large amount of I/O, order megabytes. This is larger than all of the others. And it has a high percentage of both read and write sequentiality. So we choose to call this content update. Really, the full name should be bulk content update. So content read followed by content write over a large amount of content. And of course, we can repeat this for all of the application types we identify leading to those labels. Now, those labels, you will notice there is an element of subjectiveness about them too. So what we choose to call them is a little bit subjective, but the multidimensional numerical vectors, that's not ambiguous. You might want to choose to call them different things, depend on your design case, but the numerical description is still the same. So now, design insights based on applications. So for example, this one, you will notice that the viewing human content and content update applications, they both have a large percentage of sequential access. None of the other application types have that. That's the observation. Apps with any sequential read-write at all have high sequentiality. Now, the implication there is storage clients, storage applications in this case, they can prefetch files based on sequentiality only. Prefetching means the moment an application sees sequential access to some file, it might as well fetch the entire file from the server. Subsequent access to that file, according to this, will be highly sequential. Therefore, the client application would have had the file ready even before the user requests the subsequent data. So that's one design insight. Let's do another one. So for this class of applications, you see that they do a small amount of I/O, so 1 kilobyte of I/O, and they open a few files multiple times. So the way to read that is they open 10 files 4 times. So this is a small I/O, but a large amount of repeated opens. The implication there is that clients should always cache the first few kilobytes of every file, regardless of other caching policies you have. The reason being 1 kilobyte, that's not too much to ask for in the cache, and the multiple file opens and multiple accesses, that really means if the data is already in the client cache, then subsequent opens, subsequent read or writes, that will hit the client cache. No need to bother the server. And this is important as we try to service more clients on fewer servers, and also try to keep the caching algorithms at client applications simple. And of course, that was you saw an application of that method to identify corporate application types. We can apply the same method, identical method, without any change at all to the engineering trace, and that gives us a companion table. And apologize, the font is a bit small. And of course, we can see that it's for engineering. So some of the application types, they're preserved. For example, the second cluster supporting metadata application, and also the viewing human content, those are preserved, and some of the ones are new. For example, the compile app, compilation app, an application that compiles code. You will not expect to see that in the corporate use case. Of course, if we generalize it to an application, to an engineering trace, we can also generalize this identical method without change at all to any other SIFS use cases. So if you have a SIFS use case in your organization and you want to find out what kind of applications there are, you can apply this exact same method. It's a matter of more or less pressing a button and giving it a pointer to a trace. So to give you a preview of other design insights in the paper, there are insights about consolidation, so consolidating many clients. This is important because economic incentives make us want to consolidate a large number of clients on a small set of hardware, and we need to make sure with a high level of confidence that the consolidated clients play nicely with each other and performance will not be adversely affected. Likewise, there are file delegation insights. So this is important again because if possible, the server will want to delegate files to clients. This improves both performance, that the clients will have whatever data it wants ready even before it wants it, and also it will help server performance in that the load on the server will be decreased. Likewise, placement insights. So you can imagine without this type of analysis, we will be able to think up quite complex decisions, algorithm, policies with regard to what data to place on what kind of storage medium. This concern is becoming more prevalent as SSDs, RAMs, disks, they all combine to form a complex and network storage system that need to be optimized. So the thing you notice is that these insights, they are all simple threshold-based decisions using one way of describing the system. You see the word only highlighted there multiple times. The ability to do that really comes from this multidimensional, extensive empirical analysis of the trace. That the reward of doing that analysis, if you like, is that we have a high confidence that one, the threshold-based decisions, they actually work, they will lead to a performance improvement, and that we are thresholding on the right dimensions, the right ways to describe the system. So let me give a final example of doing this empirical analysis, yielding new knowledge and help us correct our mental models about how systems behave. So the mental model we begin with is that when we ask the question what type of applications there are on these storage systems, we are thinking of binary, thinking of hardware. So in other words, when we say we want to, there may be three kinds of applications on this storage. We're thinking inevitably an Office app, a mail app, or a web app. That actually turns out to be wrong. And this is or unhelpful, sorry. This is the process we went through. So we made this graph. The way to read this is on the vertical axis is the fraction of application instance in each type of apps. So for example, this is for cluster 1 from earlier. The way you read that is 20% of the apps there, they access a file with no file extension and an Excel file. And then another 15% roughly access a file with no file extension and a doc, Microsoft Word documentation. So we do this across all of the different app types, and something enlightening or surprising, unexpected happened. So you will notice that the no file extension and Excel types, they appear in all of the application types, all of them, so on. Likewise for the doc and some of the PowerPoint, HTML, they appear in multiple app types as well. So this is telling us that it's actually unhelpful to think about app types in terms of binaries, in terms of software. And really what we need to think about is thinking about them in terms of different I/O access patterns. So this helped us correct our own mental model, and we were very surprised to find that. So just as this bit of information helped enlighten us, we hope that as you read the paper, you'll find bits of information that will be interesting to you. So summary. Our contribution is really a multidimensional trace analysis methodology. We perform this analysis at 4 semantic layers at both clients, storage clients and storage servers, detailed results in the paper. And we derive 6 design implications for each of the server and clients. Future work, of course. In this paper, we only analyze data movement patterns, and we believe there are optimizations once we start analyzing data content and working set. We will, of course, implement some of these optimizations, and we are building workload replay tools. So this is the necessity to up our evaluation methodology as well. We've been evaluating file systems using benchmarks, using selected use cases, using small-scale case studies. Now, the ability to replay these realistic workloads, that will give us confidence that whatever optimizations we do, they will survive a realistic use case, and they will translate to a realistic use case, and we're not optimizing for something artificial. Of course, the traces are available from NetApp under a non-commercial use license. All of my co-authors are here today. We will be very happy to hear your thoughts and discuss collaboration opportunities. Thank you. So, yes, sir.
Really loud.
Test, okay, better. So I'm Ymir Kusson from Reykjavik University. This is very interesting work, well presented. I have a couple of questions. First is, how many clusters did you try initially for the k-means? Because you gave us 5 and you didn't give us any error bounds or anything like that. Are there any like fuzzy clusters within your 5 clusters, or is this something that?
Yes, this is a fantastic question, and it goes to the statistical expertise required to do this kind of analysis, and it actually falls under the broader category of what the statistics community calls sensitivity analysis. So let's see, I have the exact picture. So the standard method is you want one standard method. There are several. The method we use is we actually go through several values of k. So this is a choice, a trade-off between explaining enough variance in the data and having a large cognitive load. So you can imagine in the degenerate case, we have as many clusters as data points. And that will explain all of the variance.
Absolutely.
But then you got to label, 100,000 odd clusters, and that's unhelpful. So that's one method. As you can see, there is a level of subjectiveness. You have to make this decision yourself in deciding where to stop. You want high variance, you want to get past the knee curve, but where exactly do you stop? Is it at the 80%, the 90%? There's a level of trade-off as well. With this other thing, it's quite detailed, and in fact, we choose not to even present in the paper, where we look at the tree structure in clustering, so the data point translation between each, and how the clusters split up. So that's another more thorough way of doing it. But thanks for the question. So
yeah, the second question is, we don't have to, okay, never mind. Thank you very much.
I can chat with you afterwards. Should we rotate? Okay.
It's similar, Suman-Keist. So k-means clustering assumes that quantities are of comparable, the dimensions are of comparable quantity. Why didn't you think about other methods like principal component analysis, which seems more natural to me?
Yes, that's another fantastic question, and I'm happy that we got folks with statistics specialty in the audience. So the question is, why k-means? Why not, say, PCA? That's more natural. The reason being k-mean does not make any assumption about the nature of this multidimensional space. First, we do some normalization. So normalize all of the dimensions to 0, 1 range. That's essential. That's the first part of your question. Second, the reason we don't use PCA, we consider PCA, the reason we end up not using it specifically is because within PCA, there's an assumption about multidimensional linearity. So there's an assumption about the ability of those data points to project to a linear subspace, so a hyperplane and things like that. K-means doesn't make that assumption. So identifying the multidimensional, and the second reason is that PCA gives you a vector as a principal component. Now that vector will say, 0.5, the principal vector will be 0.5 of the IO size and 0.3 of the sequentiality and 0.78 of the overwrite. So having that kind of insight is helpful, but it doesn't lead to the same kind of answers. Like these are the common types of applications. Yes, sir.
Ajay Gulati, VMware. So it seems to me that you have made this assumption that if you see some pattern in your data and you apply some optimization based on that, you would see performance improvement. Whereas to give an example, if you look at client consolidation and you said just by looking at read-write ratio, you can get better consolidation. Whereas another factor that may be critical is how are they correlated in terms of their workload in time, if clients are sending the workload together versus differently. And did you implement most of these techniques or some of these techniques to see that what you learn really leads to performance improvement?
So that's the fantastic question. Thank you. So time series analysis at the fine-grained level, we haven't looked at that just yet. I imagine you guys at VMware will have a lot of insights about that, and you will like to increase the way you describe an access pattern even further. So we looked at it from storage. You might want to also look at it from CPU, memory, various other things. So, sorry, wrong press the button. Okay, so actually let me show this. This is behavior variation over time. This is long term. This is not short term. This is not the thing you're talking about. So let's see. So we need to do that analysis. It will lead us to peak and valleys. But I think the way I will interpret that kind of data is if you have peaks in the arrival patterns, that's really not, that's really initiated from the customers. So it's out of control of the system. Then it's the responsibility of the virtualization software, module, whatever, to service that. And the insight is to understand how they arrive, what kind of peaks, whether it's just write or rewrite or sequential or so on and so forth. That will be my way of doing, one way of doing fine-grained time series analysis. That could be something we could talk about later.
I think the high-level point is that there might
no follow-ups. We have time for one more short question.
Okay.
The next speaker steps up.
Cool. I can chat with you all afterwards.
Petros Magnatis, Intel Labs. A fantastic but short question for you. So I imagine that the choice of application suites that are deployed in a particular enterprise network impacts a lot the data that you get. You don't have a random set of applications there. To what extent do you think that your insights, the design insights that you drew, would apply to a different enterprise network like Intel's or Oracle's or somebody else's with a different choice of application suites, different combination of access patterns?
I'm sorry, what was your affiliation again?
Intel.
Intel, okay, great. So my response to that will be, that's a natural question to ask. It's a generalization question about this methodology, so how do the insights translate? Right now, honestly, the honest answer is we don't know, because those are the two traces at this scale that we analyze. So I encourage all of you, in fact, if you have this type of use cases, to actually apply the same methodology and answer this question. So because the methodology is general, the insights are specific, and the design improvements they lead to needs to be tuned to the particular use case. We haven't done it yet. We don't have the data to do it yet, and this is a challenge for the field, the field in general, to come up with this kind of traces and perform this style of analysis.
Having been challenged,
Thank you.
let's thank our speakers.